Today we're going to learn about extreme values, which is 5.1 and 5.3 in your textbook, and this is going to be kind of the first application to graphs that we're doing with derivatives. So we're going to use calculus to help us define max and mins without a calculator, and in your previous math classes you've probably found max and mins using your calculator, so now we're going to do it algebraically using calculus. So to just review a few terms, and please write these in on your notes that I gave you today. So the absolute extreme values is another word for maximum or minimum points on a function. They are sometimes called global extremes. They are also sometimes called absolute extrema. So the extreme values can occur in the interior or at the endpoints of a function. Here are two examples, and they have endpoints on the first one, and it says identify the absolute min and the absolute max on the graph. So just to show, this function is x squared on a closed interval from 0 to 2, and if it says identify max or mins, we're usually going to state the point. So for the min, for the absolute min, the point is 0, 0 because that's the lowest. And then the absolute max would be 2, 4 because that's the highest point. On my second graph, we just have f of x is equal to x squared, and if they don't put arrows or if they don't put dots, then we assume it goes on forever. So this one, it has an absolute min. This is the absolute min at 0, 0. But it does not have an absolute max because the y values go to infinity. Now the key thing is the extreme value theorem. So if a function is continuous on a closed interval, then, and on your notes it says from a to b, then f has a maximum or a minimum over that interval. And there's kind of three examples, like on this one, the max and min occur on the interior points, so not at the endpoints. Here, the max and min occur at the endpoints, so this would be your max, this would be your min. And then here, your absolute max occurs inside, on the interior, and then your absolute min is at an endpoint. And you could have the reverse. You could have the absolute max at an endpoint and the absolute min in the interior. So local extrema, or they're also called relative, which is on your paper, relative extrema. So a local max or a relative max is the maximum value within some open interval, which means it's the highest value in the area of a function. And a local min is a minimum value within some open interval. And then just to review again, the global max are the highest of the local max or the highest y values. And global mins are the lowest of the local mins or the lowest y values. So we have two examples, and it says identify the extrema on the following functions, determine if they are relative or absolute extrema. So the first one, they kind of pointed them out for you, but we're going to state them. So they only give us the x coordinates, we don't have the y's, so I'm going to state it in terms of the y's. So the relative min, or mins, are at any of the places where it's the lowest on the graph in the area. So x equals a, even though it's an absolute min, it's also a relative because it's the lowest value in this area. So x equals a, x equals c, and x equals e are all relative mins. Then the lowest of them is the absolute min, which is x equals a. Then the second one, the relative max, are x equals b and x equals d, because those are the highest points in their area. And then the absolute max is the highest one, which is x equals d. Okay, so for the second example, I want you to list the max and min. So pause the video to do that, but list them as coordinates. So for example, if I do like a relative max, the first one I would list is this one, which is -5, 1. So list the point because you can find the y coordinate. So pause the video and do that, and then play when you have your answer. So you can check your answers with mine. Just notice because there's arrows and the y values go down to -infinity, there are no absolute mins. And then the relative max of 0, 3 is the highest one, so that's your absolute max. So now we're going to get into more of the calculus terms and how we find max and mins without a calculator. So the first term you need to know is a critical point. A critical point is where the first derivative is 0. So that means f prime of x is equal to 0, or undefined, or where the derivative is undefined. A lot of times they will write it as like f prime of x does not exist, or infinity. Because generally it's a constant over 0, which is like infinity. The y value of a critical point may be a local maximum or minimum. They also may be global if they're the highest max or the highest min. So critical points that have a derivative of 0 but no max or min are plateau points. And this means f prime of x is equal to 0, but the derivative does not change sign. So, and the key thing is max and min points in the interior function always occur at critical points. However, critical points are not always max and mins. They could be a plateau point. So, an example of a plateau point is kind of like this, where your function levels off, but the whole time your function is increasing, so your derivative is always positive because the slope is always positive. It could also be this way where your function's always decreasing, so your slope or your derivative is always negative, but it levels off, so f prime at this point of a would be 0. If you look back on our graph here, this is a plateau point. So the derivative at this point, we can just call it f, is equal to 0, but the function's always increasing, so the derivative is always positive and it never changes signs. So the first derivative determines where a function is increasing or decreasing. The key thing to remember is the first derivative mean slope. So if f prime of x is greater than 0, that means the derivative is positive or the slope is positive, and then a function would be increasing because the slope is positive. When f prime of x is less than 0, so that means the slope is less than 0, so the slope is negative, so the function is decreasing, and then again the slope is negative. If a derivative changes from positive to negative, so that means that the function changes from increasing to decreasing, because if my slope's positive, my function's increasing. If my slope's negative, my function's decreasing. We would have a max. And then this would be your critical point. It might also be a cusp, and again, this would be your critical point, because at that point the derivative does not exist or is undefined. So again, on this one, the derivative is here, it's greater than 0 because it's positive. And here, after the critical point, the derivative is less than 0 because the slope is negative. Here, the slope is positive, so the derivative is positive. And here, the slope is negative, so the derivative is negative, less than 0. If the derivative changes from negative to positive, so that means that you're going from decreasing to increasing. there is a min. So again, f prime of x is determined by the slope. If the slope is less than 0, the derivative is less than 0. Usually we say critical point CP, so this would be your critical point, and then on this side, the right of the critical point, the derivative is greater than 0 because the slope is positive. And again, you might also have a cusp like that, and at this point, at the critical point, the derivative is undefined. So then we're going to talk about a cusp and then also a vertical tangent, the two cases where the derivative does not exist. So a cusp occurs where the derivative is undefined, so 0 in the denominator, and the derivative changes sign. So for you to have a max or min, the curve has to switch direction, so the slope has to change direction, so the derivative has to change sign. And then remember, the secant lines on both sides of the point do not have the same slope for a cusp. The function is continuous at a cusp though, and then you can also use a corner. So for an example, it says draw a rough sketch of y equals x to the 2/3. You may use your calculator. Label the critical point and the slope as positive or negative before and after the critical point. So pause the video and find your calculator and draw a graph of x equals 2/3, and then try to figure out where the critical point is, and then if the slope is positive or negative, or the derivative is positive or negative. So if you draw your function, it looks something like this, a little bit more even on both sides. But at 0, this is your critical point. Okay, and at this point, f prime of 0 is undefined. And then from 0, or from negative infinity to 0, the slope is negative, so x prime of x is less than 0. And here f prime of x is greater than 0 because the slope is positive. So algebraically, how we show this is we would take the derivative. So if I take the derivative of x to the 2/3, I bring the 2/3 down and I subtract 1 and I get negative 1/3. And if I rewrite this to over 3x to the 1/3, to find critical points, you set the derivative equal to 0 or find where it's undefined. So if I set it equal to 0, this is never going to equal 0 because the numerator can't equal 0, but the denominator can equal 0. And if you solve for this, that would be at x equals 0. So this makes it a critical point because this is where the derivative is undefined. Now for this to help us, a lot of times we make things called sign charts. So a sign chart shows the relationship between the derivative and the original function. So what you do is you kind of draw a line for a number line, and you label your sides as f prime and f, and we usually always put f prime on the bottom, and you put your critical points on your number line. So I'm going to put 0 on my number line. Now if we can look at the graph, we can kind of fill in a sign chart from the graph. We'll do this algebraically in a few examples, but what you do is you look and see if the function's increasing or decreasing. So from negative infinity until you get to 0, my function's decreasing, which means my slope is negative. And then from 0 to infinity, my function's increasing, so I put up arrow for increasing, a down arrow for decreasing, and I put a plus because the slope is positive. So this shows the sign of the slope, and this shows what is the original function doing for f. And then generally on a number line, they put infinity when it does not exist. They might put DNE, and then they would put a cusp for what happens at f of x at the point. So this is called a sign chart, and we'll be doing a lot of stuff with that. Okay. So this is what happens when you have a cusp. The second type is a vertical tangent. So a vertical tangent occurs where the derivative again is undefined, and the derivative does not change sign. Again, at this point though, the function is continuous. So again, pause and draw a rough sketch of x to the 1/3, and then do what we did before and label your graph with the critical point and where the slope or the derivative is positive or negative. Okay, so again, here's my graph. Before x equals 0, my function is increasing, so the slope is greater than 0. After x equals 0, my function is increasing, so the slope is greater than 0. Here's my sign chart again. So I put f prime and f. F is increasing until 0 and after 0, so the slope at both of those intervals is positive, and the derivative at that point does not exist because it's a vertical tangent. If you took the derivative again, you would get 1/3 x to the negative 2/3, which is 1/3x to the 2/3. Again, never can be 0, but if you set the denominator equal to 0 to find where it's undefined, x would equal to 0. So this again is a critical point. So a key thing is a critical point must be in the domain of the function. So if we look at this example, 0 is in the original function because 0 to the 1/3 is 0. So the first step when finding critical points is always to write the domain of the original function. We didn't for the last two examples because the domain is all real numbers. But if you hit a function like a rational function, a square root function, or a log function, you should pay attention to the domain, because if you get where the derivative is 0 or undefined, but it's not in the domain, it is not a critical point. So the key thing about a cusp or a vertical tangent is to recognize when they're different algebraically. So a cusp or a vertical tangent on the original function, for both of them, f prime is undefined. How you tell the difference is by checking if the first derivative changes sign at this point. If the first derivative changes sign, then the point is a cusp, because this point is either a max or a min, since the original function changes from increasing to decreasing, or vice versa. If the first derivative does not change that sign, then this point is a vertical tangent. And again, this is only true as long as the x value exists for the original function. If not, this value is going to be a whole or vertical asymptote because it's not in the domain. A plateau point only occurs when f prime of x is equal to 0 and the derivative does not change sign. And if f prime of x is undefined and the derivative does not change sign, the point is a vertical tangent unless it's a piecewise function. You can look at page 210 to see an example of this, and also make sure the x value is in the domain of the original function. So then max and mins also occur at endpoints, so they occur at critical points or endpoints, and there's 4 examples, and this last line is not in your chart. So on here, if x equals a is a left endpoint, so on the left side, and the derivative is negative, which means that my function is decreasing, this point is going to be a max, because f of x is decreasing right. If you have the second example, if x equals a is a left endpoint, and the derivative is positive, f of a is a minimum because the function's increasing, so it's the lowest value. If x equals a is a right endpoint, and the derivative is positive to the left, which means it's increasing left to right, this would again be a max because you're increasing up to that point, so it's the highest point. And the last one, if xa is the right endpoint and the derivative is negative to the left, so it's decreasing, this point is going to be a min. So those are your 4 cases when you have endpoints, if they're max or mins. So we're going to do one example of the first derivative test, and then the rest of the stuff we will do in class tomorrow. So these are the steps for the first derivative test. There's a few notes in between you can read through, but we're going to use these steps for the first example. And on yours it has directions. It says use the first derivative test to find the local max and mins, and then the global max and mins, and state where the function is increasing or decreasing. So the first derivative test is to find max and mins, but we can use the first derivative to help us find where a function is increasing or decreasing. So step 1 is to take the derivative. So this is my function, and I'm going to take the derivative. And I get 6x squared plus 6x minus 36. The second step is set the derivative equal to 0 to find the critical points. Also find if the derivative is undefined at any x values to find other critical points. So this is not a fraction, so it will never be undefined. But I'm going to set it equal to 0. I'm going to factor out a 6. And then I'm going to factor this, so what multiplies to negative 6 and adds up to 1, which is x plus 3 and x minus 2. And then I set every term within x equal to 0, so I don't have to worry about the 6 because there's not an x, and I get x is equal to negative 3 or x is equal to 2. Now this has a domain from negative 10 to 3, so make sure both values are in your domain. If not, then cross it out. But negative 3 and 2 are both in this domain. So then it says make a sign chart with the critical values. So for a sign chart, you make a line and you label the bottom f prime and above it f for the sign chart for a first derivative. You're going to put your critical points, lowest value to the left, positive values to the right. So I'm going to mark negative 3 and 2, and I'm also going to put my endpoints. So I'm going to put negative 2 and 3. Okay, they don't have to be spaced out, and you don't have to write all the x values. You can if you want, but I'm going to put the endpoints and my critical points on my number line. At the critical points, the derivative is 0. So I'm going to put 0, and I'm going to put endpoint for f of both at negative 10 and 3. So 0 and 0. So I need to figure out if these points are max and mins. Okay, so the first derivative test we use to find max or mins. So we need to figure out if the derivative is positive or negative on both sides of negative 3 and on both sides of 2 to see what's happening with the function. So you're going to plug values in between critical values to determine if the derivative is either positive or negative for each interval. If the derivative is positive, the original function, again, we said was increasing. And if the derivative is negative, the original function is decreasing. So you can pick any value between negative 10 and negative 3, and you're going to plug it into the derivative because I want to know if the derivative's positive or negative, because if it's positive, my function's increasing. If it's negative, my function's decreasing. It doesn't matter what value. I'm just going to try like f prime of 4, or sorry, negative 4. Plug it into the factored term, because if you don't have a calculator, it makes it much easier. So I get 6 times negative 1 times negative 6, and I don't really care the value, I just care if it's positive or negative. If you want to find the value, you can, but it doesn't matter. So I have a positive times a negative, so that's going to give me a positive, which is a positive 36. So this is positive, and that means from negative 10 to negative 3, my function is increasing. So I'm going to try a value between negative 3 and 2. So I'm going to try like f prime of 0. If 0 is in your interval, always try it. If I plug 0 into this, I get 6 times 3 times negative 2. Again, all I care about if it's negative or positive. It gives me a negative, so this is negative, and it's decreasing. And then I'm going to do the same thing. I'm going to try f prime, something between 2 and 3. You can even use an endpoint as long as it's not a critical point. So I'm just going to use 3 because it's easier. So if I plug in 3 to this, I get 6 times 9 times 1. Again, all I care about the sign, which is positive. So then from 2 to 3, my function is increasing. So that is step 4. Step 5 is determine if the critical points are max, mins, plateau points, or vertical tangents. For each critical point, if f prime changes from positive to negative, the point is a max again. If f prime changes from negative to positive, the point is a min. If f prime is undefined and f is continuous and f prime does not change sign at the point, it is a vertical tangent. And if f prime is 0 and it does not change sign, then the point is a plateau point. It's just kind of reviewing all the things we just went over. You can see it if you look at this. If you would trace and you go up and then you go down, this point has to be a max. So if it changes from increasing to decreasing for the function, it's a max. From decreasing to increasing, this point has to be a min. Now you also have to check the endpoints if it's a closed interval. So these are the 4 examples we did before in that chart. -10 we're starting at, and then we're increasing. So this is going to be the lowest point. So we're going to have a min at -10. And at 3 we're going to have a max because it's increasing. So we found all the critical points, and so now we found all our relative or our local maxes or mins. So for this, I have a relative min at x equals -10 and x equals 2, and I have a relative max at x equals 3 and, -3 and x equals 2. So that's what we found using our sign chart. Now for this, they asked us also to find the global max and min. In order to find the global max and min, you have to find the y values and compare them to see which one is lower for the min and higher. So I'm going to find f of -10, f of 2, f of -3, and f of, oh, sorry, I messed up. Min here, okay, sorry, max is also at 3, x equals 3, not x equals 2. Sorry. So f equals -3 and f equals 3. So I'm going to find those 4 points. So you're just going to plug these back into the original. So if you do that, you can kind of pause to do that, but I'm going to come up to my original function, which is all the way up here, and plug them in here to get the y values to see what's the highest and what's the lowest. If you do that, -10 is 66. 2 is -42, -3 is -20, sorry, -3 is 83, and 3 is -25. Okay, and then from this, you can see that -383 is the global max. And then the global min is at 2, -42. Now you have to find the derivative, especially if you don't have a calculator, because if you look at this, 66 doesn't look like a max because it's much bigger than -42 and -25. But it is because the function's going up to 83 between there. So this makes it a relative min. But you need to find the y values to find the global. Then the last thing the question asked is find where the function is increasing or decreasing. This isn't technically the first derivative test, but my sign chart easily tells me that. So when my derivative is positive, my function's increasing. So we're going to say it's increasing from -10 to -3, and also from 2 to 3, wherever I have an up arrow. Now, for increasing, decreasing, we always put parentheses. Even though -10 is an endpoint, you can't increase unless you have 2 points to compare to. So you always put parentheses for increasing and decreasing. And then it's decreasing from -3 to 2 because it's negative slope. So we found this. So these tend to be a little bit long problems if you're trying to find them. If you have to justify, the key thing it kind of says here for sign charts on your paper. Sign charts are useful to help you determine the relationship between the derivatives and the original function. However, a sign chart can never be used as the justification. All justifications must be in words and must explain about the derivative and second derivative when explaining what is happening with the original function. And then the first derivative test must be used to determine if endpoints are max and mins. You cannot use the second derivative test, which we haven't learned yet, but we will in class tomorrow. So just kind of quickly, if you had to justify, you don't for this point, but if you had to justify like why x is -3 is a max, you would have to say that the derivative changes from positive to negative at x equals -3. Therefore, this point is a max. And if you had to justify where x equals 2 is a min, you would say the derivative is changing from negative to positive. We will practice with that for next class. So if you could try example B for next class, and then we will finish kind of the rest of the notes in class tomorrow.